Hello dear student, myself Prof. Sukhbiraj K. Today we learn some important concept in a superposition of wave. Firstly we discuss here what I mean by natural frequency. Definition: the frequency at which an object tends to vibrate when hit, plunk or somehow disturbs is known as natural frequency. Definition: the frequency at which an object tends to vibrate when hit, pluck or someone disturb is known as a natural frequency. In the vibration, the object is not under the influence of any outside force. Second one, what I mean by free vibration? What I mean by free vibration? In free vibration, the body at first is given an initial displacement and the force is then withdrawn. In a free vibration are produced when a body is disturbed from its equilibrium position and release. Okay, in free vibration are produced when body is disturbed from its equilibrium position and release. And another type of vibration is a force vibration. Second type is force vibration. Definition: force vibration are produced by an external periodic force of any frequency. In force vibration, continuous external periodic force is required. If external periodic force is stopped, then force vibration also stop. For example, vibration in a drill machine and a second washing machine. This is these two best example of a force vibration. And next turn we consider here what is meant by fundamental frequency. A definition: the minimum frequency of vibration of body is called as a fundamental frequency. Okay, the minimum frequency of vibration of body is called its fundamental frequency. And next one we consider another term here, what I mean by fundamental modes. The mode of vibration of a system in which frequency of oscillation is minimum is called as a fundamental modes. The mode of vibration of a system in which the frequency of oscillation is minimum is called fundamental modes. And next one, what I mean by overtones and harmonics. Firstly we discuss overtones, the tones whose frequency are greater than fundamental frequency. फंडामेंटल फ्रिक्वेन्सीपेक्षा जी फ्रिक्वेन्सीची टोनची फ्रिक्वेन्सी जी आहे ही काय असेल, ग्रेटर दॅन असेल, त्याला कन्सिडर करायचं ओव्हरटोन्स. नेक्स्ट, ओव्हरटोन्स आर ओनली दोज मल्टिप्लाय ऑफ फंडामेंटल फ्रिक्वेन्सी which are actually present in a given sound. The first frequency higher than the fundamental frequency is called as a first overtones. This is importance. The first frequency higher than the fundamental frequency is called as a first overtones. And next one we can consider here harmonics. What I mean by harmonics? Harmonics are simply integral multiple of the fundamental frequency. All harmonics may be present in given sound. First harmonic is the same as the fundamental frequency. And next one we can discuss here what I mean by organ pipes. Organ pipe means the pipe filled with air and which when vibrates produce sound waves is called as or is known as organ pipes. Here another definition of a organ pipe: a device in which a air column is vibrate to produce sound wave of a desired frequency is called as a organ pipe. Okay, this organ pipe can be classified into two types: First one is closed organ pipe, which organ pipe closed organ pipe, and another one is second type of a organ pipe is a open organ pipe. Firstly, we consider here what is meant by closed organ pipe. The organ pipe in which one end is open and another end is kept closed, this type of pipe is called as a closed organ pipe. And second one, what is meant by open organ pipe? The organ pipe in which both ends are open, this type is called as a open organ pipe. Okay, this is a two type of a organ pipe. And another term we can consider here, end correction. What do you mean by end correction? A definition: the distance between open end and antennode is called end correction. Repeat again this definition: the distance between open ends and antennode is called as end correction. Basically, we discuss here the antennode is not formed exactly at open ends, not formed exactly at open end, and it is a little distance behind its. According to Reynolds, to the first approximation, the end correction at an end is given by this end correction become here E is equal to 0.3 into d, small d, where small d is the small d is the inner diameter of the pipe, and capital L, L, a length of ear column, is different from the length small l of the pipe. Firstly, we calculate here for pipe close at one end, then this corrected length, this become the corrected length of ear column. Capital L is given by this capital L is equal to length of ear column in 5 and plus end correction at the open ends. Capital L is equal to length of ear column in pipe plus end correction at the open ends. Then capital L is equal to small l plus e. This is a corrected length of ear column when pipe close at one ends. Then second one, we consider here for pipe open at both ends, then the corrected length of ear column capital L is given by capital L is equal to length of ear column in pipe plus end correction at both end. Here end correction at both end, that is we can write capital L is equal to small l plus twice into e. This twice indicates end correction at both ends. Okay, then we can write here the corrected length of ear column is equal to small l plus twice e. This is a basic difference between for pipe close at one ends and for pipe open at both end. Then we calculate corrected length of a ear column in both cases. Next point we can discuss here, vibration of ear column in a pipe close at one ends. Okay, consider here long cylinder tube close at one end. It consists of an ear column with a rigid boundary at one ends. when vibrating tuning fork is held near the open ends in this way. Near the open ends of the closed pipe, sound waves are sent by the fork inside the tube. Longitudinal waves traveling along a pipe of finite length are reflected back at the end as a transverse wave are reflected as the fixed end of the string. The phase of the reflected wave depend on whether the end of the pipe is open or closed, how wide or narrow the pipe is in comparison to the wavelength of the longitudinal wave, like a sound waves. At close end there is a least freedom for the motion of air particle, thus there must be node at the close ends. This is a nodes at close ends. The particle little beyond the open end are most free to vibrate as a result. Antinode must be formed little beyond the open ends. Here is a little beyond the open ends. This is the different way in which ear column vibrate are called mode of vibration of a ear column. Okay, mode of vibration of a ear column. Firstly, we explain vibration of air column in pipe close at one ends. Firstly, we discuss for a fundamental modes. Fundamental modes. Consider this is the first diagram. Fundamental. This is a fundamental mode of vibration of air column in pipe close at one ends. First mode of vibration. First mode of vibration of air column close at one ends. Close at one ends is known as fundamental modes. Then the distance between the nodes and adjacent antinode. The distance between nodes and adjacent antinodes, this become capital L is equal to lambda by 4. The distance between nodes and adjacent antinode is lambda by 4. Then we can calculate here lambda is equal to 4L. Consider equation first here, where lambda is the wavelength of the fundamental mode of vibration in air column. If the fundamental frequency we know that the relation of velocity, frequency and wavelengths, p is equal to n lambda, then we can calculate fundamental frequency, that is n is equal to v upon lambda. Consider equation second here. Then lambda is equal to 4L. Then this equation second become n is equal to v upon 4L. Consider equation number third, and we know that L is equal to what? We calculates for a pipe closed at one ends, then corrected length of a air column is given by capital L is equal to small l plus e. Then frequency of fundamental modes, this become n is equal to v upon 4 into capital L is equal to this, and small l plus e. Consider equation 4. This is the frequency of fundamental mode, which is lowest frequency. The fundamental frequency is also known as first harmonics, hence it is a lowest frequency of vibration in ear column in pipe close at a one end. Second one for second mode or first overtones, the next mode of vibration of ear column close at one end is shown in above figure. In this figure, second figures. This second figure. Consider here first overtone for vibration. First overtone for vibration of ear column in pipe close at one ends. Here in a second mode of vibration of ear column, two notes and two antinodes are formed. Here two notes, this is the first node, this is the second nodes, and two antinodes, this is the first second antinodes. Okay. In a second mode of vibration of ear column, two nodes and two antinode are formed. The length of ear column, the length of ear column the length of ear column, this become capital L is equal to 3 lambda 1 upon 4. Then we can calculate lambda 1 is equal to 4L by 3. Consider equation 5th. Here lambda 1 is the wavelength of the waves and here 1 be the frequency of the wave. The velocity in the second mode is given by p is equal to n1 lambda 1. P is equal to n1 lambda 1. Substituting equation here n1 is equal to v upon lambda 1. Consider equation 6. Substituting equation 5 in equation 6, we gets n1 is equal to v upon 4l by 3. Rearranging this equation, n1 is equal to 3 v upon 4l. Rearranging this equation, n1 is equal to 3 into bracket v upon 4l, v upon 4l, and this become n fundamental frequency. Then we calculate here n1 is equal to Thesian. This is called third harmonics and first overtones. This is called third harmonics and first overtones. Next one, for third modes or second overtones. The next higher mode of a vibration of ear column close at one end is shown in above figure. Third modes. Consider here this diagram. In a third mode of vibration of ear column, three antinodes, first, second, and third antinodes, and three nodes, first, second, and third nodes, are formed here. In third mode of vibration of ear column, three antinodes and three nodes are formed. The length of ear column, the length of this ear column, this become 5 lambda 2 . 5 lam this length become 5 lambda 2 by force 5 lambda 2 by force. The length of your column, this become L is equal to 5 lambda 2 by force. Then we calculate lambda 2 is equal to 4L by 5. Consider equation 8. The velocity of this mode is given by V is equal to N2 lambda 2. We calculate N2. Then N2 is equal to V upon lambda 2. Consider equation 9 where lambda 2 be the wavelength of wave in third modes and N2 be the frequency of wave in a third mode of a vibration. Put equation 8 in equation 9, we gets N2 is equal to V upon 4L by 5. Rearranging this equation, N2 is equal to 5 into brackets V upon 4L. Consider equation 10 and we can write N2 is equal to 5 V upon 4 small l plus e, because small l plus e is equal to capital L's, that is a corrected length. Then we calculate N2 is equal to 5N, because N is equal to what? V upon 4L or V upon 4 small l plus e. This is called the frequency of fifth harmonics or second overtones. In this way we consider three modes of vibration. First we consider for fundamental modes, next one consider second mode for second mode of vibration, and third one we consider here for third mode of vibration or second overtones. Then we conclude here only odd harmonic are present as overtones in the case of air column vibrating in a pipe closed at one ends. Only odd harmonics are present as overtones in the case of air column vibrating in pipe closed at one ends. Firstly, we can write summary here. The relation between frequency of mode of vibration N1 as N2 as N3 is equal to 1 as 3 as 5. In general, we can write here Np is equal to twice P plus 1 into N, where N is a fundamental frequency. We calculate here P is equal to 0, then Np P is equal to 0, N0 is equal to, that is natural frequency, this become twice P put value of P, we put up 0 plus this, we calculates 0 plus 1 become 1, and N0 is equal to N, we get here natural frequency. Then we can put here once N1 is equal to 2 into 1, 2 into 1 become 2, 2 plus 1, this become 3 into N's. Here we get the relation here N1 is equal to thrice N. We get third harmonics and first overtones. In this way we complete study of vibration of air column when organ pipe close at one ends. Some question asked on this topic, these topics. Explain vibration of ear column in pipe close at one ends. Second question, show that only odd harmonic are present in the vibration of ear column in a pipe close at one end. In this way, we complete some important concept in a superposition of wave. Firstly, we discuss here what is meant by natural frequency at which objects tends to vibrate when hits pluck or somehow disturbs is known as a natural frequency. Then we consider two type of vibration, free vibration, next force vibration. Next we consider what is meant by fundamental frequency. The minimum frequency of vibration of body is called its fundamental frequency. And then we consider what is meant by fundamental modes. Next consider what is meant by overtones, harmonics, and then consider organ pipe. These organ pipe can be classified into two types. First is closed organ pipe and another one is a open organ pipe. And what I mean by end correction, end correction means what the distance between open ends and antinodes is called as a end correction. In this way we complete these points. Then we can discuss here the end correction of a pipe close at one ends. We know that the end correction means what the distance between open ends and antinodes is called end correction. That is we given corrected length of a ear column, this become capital L is equal to small l plus e. Then a is equal to hot 0.3 into d. Then corrected length of a ear column is equal to capital L is equal to small l plus 0.3 into d. In a fundamental modes pipe close at one ends, then we gets v is equal to n lambda, and we calculate lambda is equal to 4l. Hence v is equal to 4nl. Consider equation second. Then substituting equation first and equation seconds. In equation seconds we gets v is equal to what 4n and 4n and l we can put up here small l plus 0.3 into d. We knowing n small l and d, we determine the velocity of sound in ear column at a room temperature in this formula, that is v is equal to 4n into small l plus 0.3 into d. But we know that v is equal to 4 n1 l1 is equal to 4 n2 l2. Here 4 gets cancelled. Then we can put of l1 is equal to capital L1 is equal to small l1 plus e, and l2 is equal to small l2 plus e. Then this equation become n1 into l1 plus e, n2 into l2 plus e. Multiplying this term we can write here n1 l1 plus n1 e is equal to n2 l2 plus n2 e. Rearranging this equation we collect the term n1 L1 minus n2 L2 is equal to n2 E minus n1 E. Then we can find end correction. Then n1 L1 minus n2 L2 is equal to, take common E here, remaining what E is equal to, take E outside the brackets, then remaining what n2 minus n1 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 we find E, then n1 L1 minus n2 L2 upon n2 minus n1, or we can write this term E is equal to n2 L2 minus n1 L1 upon n1 minus n2. Here some question asked on this topic. Show that the end correction of a pipe closed at one end is given by E is equal to n2 L2 minus n1 L1 upon n1 minus n2. In this way we complete this point. Today we stop here. Thank you.